All right, let's do some radiometric dating calculations. On the back of, where is it? This one. On the back of your radiometric dating note sheet, there are some questions. Now notice, I will always give you this table. You do not have to memorize this table. Some students get kind of confused with the table. All it's telling you is that this parent isotope, carbon-14, breaks down into nitrogen-14. This parent isotope breaks down into this one. This one breaks down into this one, and so forth. These break down into the daughter isotope over this amount of time. This is how long one half-life is, just one. One half-life of uranium-235 is this. Remember the definition of half-life, the amount of time it takes for half of the original mass of the parent isotope to break down, right? Now this table over here, you don't really have to worry about it. It's just telling you that, if you find something that's more than 10 million years old, you probably don't want to use carbon-14 to do it because, it breaks down relatively quickly. So you can really only use it to date things up to 50,000 years old. Don't worry about this table. It's just to tell you, if you find a really, really old rock, here are the things that you could use to figure out the age of them. All right, let's get to work. It says that a rock was analyzed using potassium-40. So it was using this one, potassium-40. Okay. If the rock had only 25% of the potassium-40 left, so at 25% of the parent isotope left, how many half-lives have passed? Cool. So we got 25% left of the parent isotope. Here's what I suggest you do all the time for every single one of these kinds of questions. Make this table that I'm making here. We're going to put the percent of the parent isotope, which is what Pi is, right? Parent isotope equals Pi, in case you weren't listening when I just said that and you forget, it's over here. We want to put half-lives here, HL, obviously half-lives, HL, and then we want to put time. So we always know that in the very beginning, right, let's go back to this. When a rock is first formed, let's say it's lava coming out of the earth and it solidifies and all the minerals and elements kind of turn into rock, we know that every single rock, no matter what, is going to start with 100% of its parent isotope, and that is after no half-lives have gone by and no time. Half-life is the amount of time it takes for it to break down by half. Well, this isn't broken down at all, so no half-lives have gone by, which means that no time has gone by. This is a brand new rock, all right? Now, what you can do is you don't even need to have any question at all. You already know that, right? If the definition of half-life is the amount of time it takes for the parent isotope to break down by half, then we already know that after one half-life, there's going to be 50% of the parent isotope. After two half-lives, there's going to be 25%, right? Because 100 broken down by half is 50%. 50% broken down by half is 25%. 25% after another half-life, 3 half-lives, it's going to break down again into 12.5%, right? And we can keep going. Half of 12.5 is 6.25. This can go on forever. So without even looking at the question at all, you don't have to worry about this. This table, you can set this up every time. All right? The only thing that's going to be different is how much time went by, because each different isotope, like for this example, potassium-40, it has a half-life of 1.3 billion years, right? So the only thing different about this table for every question is going to be how much time went by, because every different element or isotope has a different half-life time. But let's go back to the question. It says, how many half-lives have passed? Well, if it has 25%, let's look at the table. 1 passes, there's 50% left. 2 passes, 25%. So we know for a fact that in this example, 2 half-lives have passed. Now we have to use a little bit of math and logic, right? How long did the rock form? Well, 2 half-lives passed. We know that 1 half-life of potassium-40 is 1.3 billion years. So we know here, after 1 half-life, 1.3 billion years. Oh, I'm using a different thing. Let's go back to this. We know that this took 1.3 billion years. And then we know after 2 half-lives, another 1.3 billion years went along, so we can add it together. 1.3 plus 1.3 is, that one, 2.6 billion years. We could keep going, but we don't have to. Why don't we have to? Because the problem tells us that there's 25% left, and we know that since potassium-40 has a half-life of 1.3 billion years, if 2 of those half-lives go by, 1.3 times 2, or 1.3 plus 1.3, we know that this rock is 2.6 billion years old. Oh, my computer's lagging. Those are your 2 answers. Very easy. You can pause now, or you can keep watching. Let's do the next one. I'm going to do all of these right now, so this video might be kind of long, but you can fast forward and pause. Time for this one. You found an arrowhead in your backyard and analyzed it, the surrounding rock, using carbon-14. So now we're using, let me clear this. We want to use carbon-14, so we're focusing on this one. Okay. The rock had 50% of the carbon-14, so it has 50%. Let's go back to our table, right? We can still use the same table. The only thing is, let's get rid of this, because this is stuff for potassium-40. I'm going to pause and come back when I'm done. All right, so I have it set up. So the problem says that we have 50% of carbon-14 left. Without even going any further, we know 50%, only 1 half-life is going by. So we're right here. 1 half-life is going by. So what are they going to ask us? How many half-lives have passed? Simple. 50% left, 1 half-life. 1 HL, 1 half-life. That's the first answer. How old is the arrowhead? Well, 1 half-life went by. We use the table. Carbon-14, 1 half-life is 5730 years. If only 1 went by, we know that. That's how old it is. So 5,730 years old. Simple, right? Let's go to the next one. Clamshell fossils found in a quarry, radiometric dating using uranium-235. So we know we're not using 238, we're using 235, this one here. And it was determined that the clamshell has undergone 5 half-lives. 5 half-lives. Let's go back here. Whoops. We didn't even do 5 yet, but we can. So 5 half-lives go by. This is 5. 6.25 divided by 2 is going to be 3.125. 3.12. We can figure this out without even knowing anything about the problem. This stuff over here is always going to be the same. So 5 half-lives went by. It wants to know what is the percent sample and how old is it? Well, the percent sample after 5 half-lives, it halved, 100% halved, then half, then half, then half, then half, 5 times, 1, 2, 3, 4, 5. We have 3.125 left. So that's easy. We know that we have 3.125% left of the parent isotope. You can write PI, parent isotope. Now we got to figure out how old it is. And we know that we're using uranium-235, which has 710 million years as 1 half-life. So we can fill this in here. I have a calculator in front of me. So 710, 1, 2, 3, 2, 3. Whew. Okay, let's get a calculator. A lot more. So we have 710, 1, 2, 3, 1, 2, 3, plus 710, 1, 2, 3, 1, 2, 3. It's going to equal this. 1,000,000,042. 1,420,000. Sorry, million. Then we're going to add another 710 of that because you know that a half-life takes that long for that specific isotope. So we're just going to keep on going with that one. Add another one. Whoops. Plus 710. 1, 2, 3, 1, 2, 3. 21. What you might notice, though, is that I'm taking a long time to do this. 2.13. What you could also do is just, if you know that 1 half-life equals 710 million, and 5 went by, we could just multiply it by 5. Save ourselves a lot of time, right? So let's get 710. That's 710,000 million. And then we'll do times 5. Whoops. Times 5. Got 1, 2, 3. That's 1,000 million billion. 3.550. So we know our answer. 3.55 billion years old. That's the answer for this question. It's going to be 3.5 billion years old. I don't want to save that. Billion years old. I'm going to do this last one really quick because it's always the same stuff, right? We go back to here. I'm going to erase this and come back. All right, let's do this last one. I'll clear this. Cool. It says a well-preserved woolly mammoth is found in a glacier. Tests determine the mammoth fossil has a C14 level, so we know we're going to use carbon-14, C14. 12.5. So let's mark that first. We know we're going to use carbon-14. And it says that it has 12.5%. How many half-lives occurred? This is easy, right? Practice makes perfect. Or I guess I should say practice makes progress. We know for a fact that if it has 12.5, that 3 half-lives have gone by. So easy. So 12.5, that means that how many half-lives have occurred? 3 half-lives. How old is it? Well, very simple. How long is 1 half-life? 5,730. You have 2 options. You can start writing it in here, 5,730. Get your calculator out, add another 5,730, then another. Or we could just do it simple. If we know 1 half-life is 5,730, and we have 3 that go by, multiply it by 3. Right? Let's see if that math I just did is correct. It is. So we know that the sample is 17,190 years old. Boom.